Okay, now let's start with the methods that are available to find the roots of the polynomial. Okay, you are already familiar with the polynomials. Now let's take a look at the methods. Now you are already introduced to some of the methods in the previous labs. For example, in the first lab, we saw the bracket approach. The bracket approach. There are two methods in the bracket approach. One was the bisection method. Another was the false position method. In the later labs, you saw some other methods like fixed point iteration. Then we saw Newton-Raphson method. Then we have the second method that you saw in the last lab. Now, several methods, these methods are developed because these methods have some drawbacks. Okay, some of the methods have some drawbacks, some limitations. To get around those limitations, okay, new methods are developed. Okay, now for example, what kind of limitation? Say for example, in the bracket method, so when you are trying to apply, so first we have a curve like this. So in the curve, the x-axis point, this is my root, the root of this equation, root of this curve. Okay, so what we are trying to do in bracket is that we try to assume an approach like this. Okay, an envelope. Okay, say for example, from 12 to 16, we assume that within this range the root is available. Okay, this was the assumption initially made using the graphical approach or any other way. Now, so we are assuming that the root is lies within this range. Then we tried some method to convert it into this point. The more iteration we get, the more iteration we make, the closer we get. Okay, this was the bracket approach. Okay, using the sign change, we are using sign change. The condition was given on the based on the sign change. Now, one thing is that, as you can see, 12 and 16. Okay, this is only valid for real roots. Okay, this kind of sign change, okay, we can only make it possible, we can only make the code possible when there is a real root available, when the roots are only real. Okay, real roots. This method will not work for real roots, it will work, but for complex roots this method won't work. Okay, this method would fail, so we need some new method. Now, among other methods, for example, in the Newton-Raphson method was a nice method. Using Newton-Raphson method, you can calculate the real roots as well as the complex roots. Okay, but you need to be careful. Later in the last lab, you saw the second method. Okay, now there are some other methods that are actually developed that can actually find the roots, the real as well as the complex roots, much more efficiently. Okay, two such methods that we are going to solve, that is the Muller method is one, Muller approach, Muller method. Another one is the Beer-Stroh method. Beer-Stroh method. Now, so we'll start with the Muller approach, the Muller method. Okay. Now this Muller method is actually quite similar to the second method that you learned. Okay. So what was the second method? In the second method, yeah. Okay. Now say I have a curve like this. Okay, I have a curve like this. Okay. So if you remember from the first lab, from the first lecture, okay, this is the valley and this is the peak point, right? Okay, this is a polynomial equation. Say for example, we assumed 2 points. First we assume 2 points and we drew a line that goes through that point. If we draw a line like this, then this is the point, this is the root that this line is actually identifying, but my original root is actually lying here. Okay, we can tune our assumption by further iteration. We can actually make the line closer to this line, this point, our original root. This is the second method. So in the second method, so if we write here, In the second method, you are using line. But what we'll do in the Muller method, what we're going to do, instead of using a line, we'll try to use a parabola. Okay. Now, the equation of the line was like this: y is equals to mx plus c, right? So, from your intermediate knowledge, you know that to find this equation, the equation of a line, you need 2 points. Okay. But to find the equation of a parabola, you need 3 points to identify equation, because there are 3 coefficients: ax square plus bx plus c. So a, b, c, that are 3 coefficients that are available. So to find the 3 coefficients, you need 3 points. So if we come here, say for example, this is our curve. Okay. So this is our root. So what we are going to try to do is that first we have to take 3 points. Okay, so to create a parabola, I have to assume 3 points. So let's name it x0, x1 and x2. I have to make an initial assumption. Okay, we'll go into details later. Just to give you some introduction first. Say for example, these are taken as 1, 2 and 3. So say this is my 1, this is my 2 and this is my 3. Okay, so this is my 1, this is my 2, this is my 3. So what I'm going to do is that on this point I am going to check which point in the curve these initial assumptions are locating. So these are the 3 points. So what I'm going to do next, let me make it a bit more clear. Okay, so it will be much more easier to draw. So this is my point, this is my point, this is my point. So I have 3 points. So I am going to plot a parabola. That goes through this point, through this 3 point. Okay, so this is my parabola. The shape is not good, but it will work. So just understand. So from the assumption, I am trying to fit a parabola through this 3 point. Okay, so once I do that, as you can see, this is crossing the x-axis and this point, this is crossing the x-axis and this point. So these 2 points are our choice. This parabola is saying that this is one root, this is another root, that is possible root. Okay, next iteration, what are you going to do? I am going to this point, say for example the point that is closer to the x-axis, will take 1 point. Let's take it here, and to this point I will check this point. I'll forget the first point and take this 3 point. Okay, then I'm going to draw another parabola that goes through this 3 point. Okay, as you see, as you iterate further and further, as you can see, our parabola is going to get closer and closer to our destination. This is our destination. This is the root of this curve. These are polynomial. So the further we iterate, the closer we get to the root. Okay, and the difference is that instead of fitting a straight line in a curve, because the polynomial shape is a curve, so fitting a straight line is not a good approach. Since our curve of the equation, curve of the polynomial is already a curve, fitting a parabola actually provide you better result. Okay, so that's why this Muller approach is actually works better than the second approach. In the second method, this Muller method will perform better. Okay, now if you don't understand, if you haven't understand this concept, how it is working, don't worry, later on we'll see more and more further. This is just the introduction. Okay, let's go into details and see how we can actually do that, how to actually go into the process. Okay,